What if I told you that right now, in laboratories around the world, physicists are trying to create something that sounds impossible? Matter made entirely out of light. Not matter that emits light, not matter that reflects light, but matter that is light. Solid, tangible stuff constructed from the very thing that has no mass, no substance, and travels at the fastest speed possible in our universe. Here's what will blow your mind. This isn't science fiction. In 1934, two physicists named Gregory Breit and John Wheeler predicted this could actually happen. They described a process where two particles of light photons could collide with such intensity that they transform into matter. Real, physical matter with mass. They called it the Breit-Wheeler process, and for 90 years, it remained one of physics' most tantalizing predictions. Why? Because creating it requires conditions so extreme, so violent, that they only exist in the hearts of supernova and near the event horizons of black holes. But in 2014, scientists at Imperial College London figured out how to do it. They designed an experiment that could actually create matter from pure light in a laboratory. And in 2021, researchers at Brookhaven National Laboratory took the first steps toward making it real, detecting the fingerprints of this light matter in collisions that generated temperatures over 100,000 times hotter than the core of our sun. Think about that for a second. We're talking about taking the most ethereal, weightless thing we know, light itself, and forcing it to become solid matter. It's like trying to build a house out of rainbows or forge a sword from moonbeams. And yet, it's not only possible, it's inevitable under the right conditions. This discovery challenges everything you think you know about reality. Because if light can become matter, and matter can become light, then what is anything really made of? What's the difference between the solid chair you're sitting on and the light illuminating the screen? And if we can create matter from light, what does that mean for the origin of everything in the universe, including you? Over the next nearly 3 hours, I'm going to take you on a journey that will completely transform how you see the world around you. We're going to explore one of the most profound questions in all of physics. Can pure energy become physical substance? And the answer is going to blow your mind in ways you can't even imagine yet. But before we dive in, do me a favor. Hit that like button and subscribe to the channel. I want to know where you're watching from and what time it is. Where you are right now, drop it in the comments. Are you in Tokyo at 3 a.m., unable to sleep because you're fascinated by physics? In New York at lunch break? In Mumbai after dinner? Let me know, because this community spans the entire planet, and I love knowing we're all thinking about these mind-bending concepts together, regardless of where or when we are. Let's start with something you think you understand: light. You've been seeing it your entire life. It bounces off objects, enters your eyes, and creates the world you perceive. Simple, right? Wrong. Light is one of the most bizarre, counterintuitive things in the entire universe. And understanding what it really is will be our first step toward grasping how it can become matter. Here's the thing most people don't realize. Light isn't really a thing at all in the way you normally think about things. It has no mass. Zero. If you put a beam of light on a scale, it wouldn't register anything. And yet, light carries energy and momentum. It can push things. In fact, there are proposals for spacecraft with solar sails that would be pushed through space by nothing but light pressure from the sun. Think of it like this. Imagine a ghost that can punch you. It has no physical body. It weighs nothing. You can't grab it or hold it, but it can still transfer force to you. That's essentially what light is. An entity with energy and momentum, but no mass. Now here's where it gets really strange. Light doesn't experience time at all. From a photon's perspective, if it could have a perspective, it exists for exactly 0 seconds. The moment it's created to the moment it's absorbed is instantaneous, no matter how far it travels. A photon that left the Andromeda galaxy 2.5 million years ago and just now enters your eye? From its perspective, no time passed at all. The physicist who figured much of this out was Albert Einstein, and in 1905, he published a paper that would change everything. It wasn't his famous E equals mc paper that came later the same year. This was about something called the photoelectric effect, and it earned him the Nobel Prize in Physics in 1921. Here's what Einstein discovered. Light doesn't just act like a wave, spreading out through space like ripples in a pond. It also acts like a particle, a discrete little packet of energy he called a light quantum. Later, these would be named photons. When light hits certain metals, it can knock electrons loose, but only if the light has enough energy per particle. It doesn't matter how bright the light is overall. What matters is the energy of each individual photon. This was revolutionary because it meant light has this bizarre dual nature. Sometimes it behaves like a wave. It can diffract around corners, interfere with itself, create patterns. Other times it behaves like a particle bouncing off things, being absorbed or emitted in discrete chunks. This wave-particle duality is at the heart of quantum mechanics, and it's absolutely essential to understanding how light can become matter. But here's what will blow your mind. Matter has the exact same duality. An electron, which definitely seems like a particle, can also behave like a wave. In 1927, Clinton Davison and Lester Germer fired electrons at a crystal and watched them create an interference pattern, something only waves can do. This means at the quantum level, the distinction between what we call light and what we call matter is already getting blurry. Think of it like this. Imagine you're watching someone dance. Sometimes they're jumping discrete, particle-like movements. Sometimes they're flowing smoothly wave-like motion. The dancer is both, depending on how you look at them. Light and matter are both dancers, performing the quantum choreography of reality itself. So if light can act like matter and matter can act like light, then maybe they're not as different as we think. Maybe they're two sides of the same coin. And that brings us to the most famous equation in all of physics. E equals mc. Einstein's equation E equals mc is probably the only physics equation most people know. You've seen it on t-shirts, in movies, referenced in pop culture. But do you really understand what it means? Because understanding this equation is the key to understanding how light can become matter. E equals mc squared. Energy equals mass times the speed of light squared. Let me unpack what that actually tells us about reality. First, energy and mass are equivalent. They're interchangeable. Mass is just extremely concentrated energy, and energy can manifest as mass. The c squared part, the speed of light squared, is just a conversion factor, like the number you use to convert miles to kilometers. But because the speed of light is so enormous, about 300 million meters per second, when you square it, you get an absolutely gigantic number. What this means is that even a tiny amount of mass contains a staggering amount of energy. 1 kilogram of matter, about the weight of a textbook, contains about 90 quadrillion joules of energy. That's roughly the energy of the atomic bomb dropped on Hiroshima, times 2,000. Think of it like this. Matter is frozen energy. It's energy locked up in a form that moves slowly, that has substance, that you can touch. And energy is melted matter that's been liberated, allowed to move at the speed of light, transformed into its most fundamental form. This equation explains nuclear reactions. In a nuclear power plant or an atomic bomb, a tiny fraction of mass is converted into energy, and the results are tremendous. In the sun, hydrogen nuclei fuse into helium, and the helium weighs slightly less than the hydrogen that went into it. Where did that missing mass go? It became light, the sunlight, that warms your skin and illuminates your day. But here's the really mind-bending part. The equation works both ways. If E equals mc, then m equals ec. If you have enough energy, you can create mass. You can create matter from pure energy. And since light is pure energy, that means you can, in principle, create matter from light. This isn't just theoretical speculation. We see it happen all the time, just not with pure light. It's called pair production, and it was first observed by Carl Anderson in 1932. Here's how it works. A high-energy gamma-ray photon, very energetic form of light, passes near an atomic nucleus. The electric field of the nucleus provides a way for the photon to transform, and suddenly, pop, the photon vanishes, and in its place appear two particles, an electron and its antimatter twin, a positron. One photon goes in, two particles of matter come out. Light becomes matter right before our eyes. Anderson won the Nobel Prize in Physics in 1936 for discovering the positron, and his work confirmed that Einstein's equation wasn't just elegant mathematics, it was a description of reality. But here's the catch. In pair production, you need that atomic nucleus nearby. The photon can't transform on its own. It needs something to interact with, something to provide momentum conservation. The nucleus acts like a backstop, allowing the conversion to happen. What Gregory Breit and John Wheeler proposed in 1934 was something even more remarkable. Two photons colliding with each other, no nucleus required, and creating matter purely from their interaction. This is the Breit-Wheeler process, and it's never been directly observed in a laboratory setting until very, very recently. Let me tell you about the paper that changed everything. In 1934, Gregory Breit and John Wheeler were young physicists working on understanding the quantum world. Breit was at New York University. Wheeler was at Princeton. And together, they published a paper in Physical Review titled Collision of Two Light Quanta. The paper was only 4 pages long. 4 pages that predicted something remarkable. If two photons had enough energy and hit each other just right, they could annihilate and produce an electron-positron pair. Matter from light, no nucleus required. Pure photon-photon collision, creating tangible particles with mass. The physics is actually quite elegant. Energy must be conserved. You can't create or destroy it. Momentum must be conserved. Particles moving before a collision must have the same total momentum as particles moving after. And various quantum numbers properties, like electric charge, must also be conserved. A photon has energy and momentum, but no mass and no electric charge. An electron has mass, negative charge, and momentum. A positron has mass, positive charge, and momentum. If you create one electron and one positron from two photons, the charges cancel out. Negative plus positive equals 0. Mass is created from energy, E equals mc, and if you do the math right, momentum is conserved too. It all works perfectly on paper. The equation balances. The quantum rules are satisfied. There's absolutely no reason it shouldn't happen. Except for one tiny problem. The photons need to be incredibly energetic, and they need to hit each other head-on with precise timing. We're talking about photons with gamma-ray energies, which means each photon needs to have energy equivalent to the mass of an electron. And two of these incredibly energetic photons need to collide with each other, not with matter, but with each other, in empty space. Think of it like this. Imagine trying to make two bullets collide in midair. Not just approximately collide, truly hit each other head-on with such precision that they fuse together. Now make those bullets massless, moving at the speed of light, and give them only a tiny chance of interacting, even if they do meet. That's the challenge. For 80 years, the Breit-Wheeler process remained a theoretical curiosity. Physicists knew it was possible, but actually doing it in a laboratory seemed impossible. The conditions required were too extreme. You'd need light sources of incredible intensity, timing precision measured in femtoseconds, that's quadrillionths of a second, and detectors sensitive enough to catch the electron-positron pairs when they appeared. But then, in 2014, something remarkable happened. Oliver Pike and his colleagues at Imperial College London published a paper in Nature, Photonics, with the title, "A Photon-Photon Collider in a Vacuum Hole-Round." They had designed an experiment that could actually do it, actually create matter from light using the Breit-Wheeler process. Here's how their design works, and trust me, it's mind-blowing. They proposed using one of the world's most powerful lasers to create a flood of high-energy photons. Then they'd shoot those photons into a tiny gold can, the Hohlraum, mentioned in the title, which is German for hollow space. Inside this can, they'd create a bath of thermal radiation, essentially a photon gas, light so dense and energetic that it's like a soup of pure energy. Then they'd fire a second laser to create a beam of electrons, accelerate those electrons to nearly the speed of light, and slam them into the photon soup. When a high-speed electron collides with a photon, something called inverse Compton scattering can occur. The photon gains energy from the electron, becoming a gamma ray. And some of these gamma rays would then collide with other photons in the soup, triggering the Breit-Wheeler process. Photon meets photon. Both vanish. Electron and positron appear. Matter from light. The Imperial College team calculated that they might create about 100,000 electron-positron pairs in a single shot. That might not sound like much. It's only about 0.000000000 grams of matter, but it would be direct, unambiguous proof that the Breit-Wheeler process works. It would be matter created from pure light, something that's never been done before in human history. As of my recording this, that exact experiment hasn't been completed yet. But here's what will blow your mind. In 2021, physicists at Brookhaven National Laboratory did something remarkably similar, and they may have already seen the Breit-Wheeler process in action. The Relativistic Heavy Ion Collider at Brookhaven National Laboratory in New York is one of the most powerful particle accelerators on Earth. Unlike the Large Hadron Collider, which smashes protons together, RHIC collides entire atomic nuclei, usually gold ions, at speeds approaching the speed of light. When two gold nuclei miss each other by a hair's breadth, passing within femtometers of each other, that's millionths of a billionth of a meter, something extraordinary happens. Each nucleus carries 79 protons, giving it an electric charge of plus 79. When something with that much charge moves at nearly the speed of light, it creates an electromagnetic field so intense that it can be thought of as a cloud of virtual photons. Think of it like this. Imagine two cars speeding past each other on a highway, so close their side mirrors almost touch. Now imagine each car is dragging an enormous net that billows out behind it. As they pass, those nets might entangle for just an instant. That's what happens with the gold nuclei. Their clouds of virtual photons can interact. In 2021, the STAR collaboration at RHIC, that stands for Solenoidal Tracker at RHIC, published results that shook the physics world. They had detected electron-positron pairs being created when gold nuclei passed near each other, and the characteristics of these pairs suggested they were created via photon-photon collisions, the Breit-Wheeler process. Here's why this is incredible. These photons weren't real photons in the normal sense. They were virtual photons, quantum fluctuations in the electromagnetic field surrounding the gold nuclei. According to quantum mechanics, energy can be borrowed from the vacuum for extremely short periods of time, creating virtual particles that pop into and out of existence. Usually these virtual particles don't have enough oomph to create real, lasting effects. But when two gold nuclei pass each other at 99.995% of the speed of light, their virtual photon clouds become so intense, so energetic, that the virtual photons can interact strongly enough to produce real electrons and real positrons. Virtual light becomes real matter. The team, led by physicists like Daniel Brandenburg and Zhangwu Su, measured thousands of these electron-positron pairs and analyze their properties, their energies, their angles, their distributions. Here's what will blow your mind. Electrons and positrons aren't the only particles you can create from light. They're just the easiest because they're the lightest. But if you have enough energy, and I mean truly staggering amounts of energy, you can create anything. This happens all the time in particle accelerators like the Large Hadron Collider at CERN in Switzerland. When protons collide at near light speed, their kinetic energy is so enormous that it can materialize as matter, not just electrons and positrons, but particles hundreds or thousands of times more massive. In 2012, physicists at the LHC discovered the Higgs boson, a particle that's about 125 times heavier than a proton. They created it by smashing protons together with such violence that the pure energy of the collision became matter. The Higgs boson existed for about a sextillionth of a second before decaying, but it was real. It had mass. It interacted with detectors. It was matter conjured from energy. Peter Higgs and Francois Englert, who predicted this particle back in 1964, won the Nobel Prize in Physics in 2013 for this work. And what their discovery proved is that energy and matter really are completely interchangeable. If you have enough energy, you can create any particle allowed by the laws of physics. But here's the catch. To create heavier particles, you need more energetic photons. An electron has a mass equivalent to about 511,000 electron volts of energy. A proton is about 938 million electron volts. A Higgs boson is about 125 billion electron volts. To create these particles directly from light, your photons would need to carry that much energy each. Think of it like this. Creating an electron-positron pair from light is like using a bow and arrow to knock over a tin can. Creating a proton-antiproton pair from light is like using that same bow to knock over a car. Creating a Higgs boson from light is like using it to knock over a skyscraper. You need exponentially more energy. The most energetic light we can produce in laboratories today, using lasers like the ones at the National Ignition Facility or the European XFEL, can reach energies where creating electron-positron pairs becomes possible. But creating protons? Higgs bosons? We're not even close. Nature, however, does this all the time. In the universe's most violent events, supernova explosions, gamma-ray bursts, collisions near black holes, photons with incredible energies are produced. These photons can and do create particles of all types when they collide with each other or with background radiation. In 2019, astronomers detected the highest energy photons ever recorded coming from the Crab Nebula, a supernova remnant 6,500 light-years away. These photons had energies up to 450 trillion electron volts. At those energies, light can create not just electrons, but potentially much heavier particles. And this raises a profound question. Is this how the universe works at its most fundamental level? Is matter just frozen light, energy that's been locked up in particle form? Is everything in the universe, the atoms in your body, the planet you're standing on, the stars in the sky, just light that's been transformed? The answer is yes. And understanding why will completely change how you see reality. Let me take you back to the beginning. Not your beginning, not humanity's beginning. The beginning. The moment when the universe itself was born about 13.8 billion years ago. In the first fractions of a second after the Big Bang, the universe was so hot and so dense that particles as we know them couldn't exist. The temperature was over 10 trillion degrees Celsius, millions of times hotter than the core of the sun. At those temperatures, matter and energy were completely interchangeable, constantly transforming back and forth in a chaotic dance. Photons would spontaneously create particle-antiparticle pairs. Those particles would immediately annihilate back into photons. Creation and destruction happened trillions of times per second everywhere in the infant universe. Matter and light weren't separate things, they were a primordial soup. a plasma where everything was everything. This era is called the quark-gluon plasma phase, and physicists are recreating tiny portions of it in particle colliders like RHIC. When gold nuclei collide at near light speed, they create temperatures even hotter than the core of the sun for brief instants, allowing scientists to study the conditions that existed microseconds after the Big Bang. As the universe expanded, it cooled. Think of it like steam condensing into water, then water freezing into ice. As temperatures dropped below certain critical thresholds, particles started to stick around longer. First, quarks combined into protons and neutrons. Then electrons stopped annihilating with positrons because there wasn't enough thermal energy to keep creating new pairs. But here's the fascinating part. There was slightly more matter than antimatter. For every billion antiparticles, there were 1,000,000,001 particles. When all the particle-antiparticle pairs annihilated, that tiny excess remained. Every atom in the universe today, every star, planet, and person came from that 1 in a billion imbalance. Nobody knows why this asymmetry exists. It's one of the biggest unsolved mysteries in physics. But what we do know is this: you are made of light. Not metaphorically, literally. The protons in your body were created when photons transformed into matter in the first microseconds of the universe. The calcium in your bones, the iron in your blood, the carbon in your DNA, all of it was forged in stars through nuclear reactions that converted light into matter and matter into light. You are reconstituted starlight, energy that's been cycling through matter and radiation for billions of years. Think about that. Every atom in your body was once pure energy. Before it was part of you, it was photons. Before that, it was particles in a star. Before that, it was photons again. Before that, it was particles in the Big Bang. And before that, in the very first instance of creation, it was pure, undifferentiated energy. You are not separate from light. You are light, temporarily frozen in a form that can think and wonder and ask questions about the universe. And that brings us to one of the most mind-blowing concepts in all of physics: photonic matter. What if I told you that light itself, pure, massless photons, could be made to act like matter? Not by converting into electrons and positrons, but by remaining as light while behaving like a solid substance? This sounds impossible. Photons don't interact with each other under normal circumstances. If you shine two laser beams at each other, they pass right through without affecting each other. Light and light don't collide, they coexist. That's why you can see in a room illuminated by multiple light sources, all those beams of light mixed together without creating chaos. But in 2013, researchers at MIT and Harvard did something that shocked the physics world. Mikhail Lukin and Vladan Volotu led a team that managed to make photons bind together into molecules. Not particle molecules, but photon molecule structures, where individual light particles became attached to each other, acting as a single entity. They did this using a medium called a Bose-Einstein condensate, an exotic state of matter that only exists at temperatures just above absolute zero. They shot photons through this ultra-cold cloud of rubidium atoms, and something remarkable happened. The photons slowed down, not just a little, but dramatically, from 300 million meters per second to about 100,000 times slower. And as they slowed, they started interacting with each other through the medium. Two photons entered the cloud separately. They exited bound together, like a molecule. The researchers could measure the binding energy, the way the photon pair moved, its properties. It behaved like matter, like a particle, with mass and structure, even though it was made entirely of light. Think of it like this. Imagine two ghosts who can't normally touch each other, passing through walls and through each other without interaction. But then they enter a special room where suddenly they can hold hands, dance together, act as a pair. That's what happened with these photons. The media went crazy with this discovery, comparing it to lightsabers from Star Wars beams of light they could clash against each other like solid swords. That comparison is a bit sensationalized, but the underlying physics is genuinely revolutionary. This is called photonic matter, or photon bonding, and it represents a completely different way for light to become matter-like. Instead of photons annihilating and creating particles with mass, the photons themselves organize into structures that have material properties. Since 2013, researchers have pushed this even further. In 2018, scientists created photonic molecules with more than 2 photons bound together. In 2020, they demonstrated photon-photon interactions in optical fibers. The field is exploding with possibilities. Why does this matter? Because if we can make light behave like matter without converting it into particles, we might be able to create structures made entirely of light. Imagine materials that are as solid as steel, but made of nothing but photons. Materials that could be turned on and off with a switch. That would weigh nothing. They could pass through normal matter when deactivated. We're talking about programmable reality. Matter that exists only when you want it to exist. Structures built from pure energy. This isn't just theoretical speculation. Photonic matter has practical applications in quantum computing, where photon-photon interactions could create logic gates and processing elements. It has applications in communications, in energy storage, in materials science. And it forces us to ask an even deeper question. What is matter really? Let's step back and think about what we've learned. Light can become matter through the Breit-Wheeler process, photons colliding and creating electrons and positrons. Light can also act like matter when photons bind together in special conditions. And matter can become light through annihilation or nuclear reactions. So what's the actual difference between matter and energy? What makes something matter versus pure energy? The traditional answer is mass. Matter has mass. Energy doesn't. An electron has mass. A photon doesn't. Simple, right? Wrong, because mass itself is just another form of energy. Remember E equals mc? Mass is energy. When you hold a rock in your hand, what you're really holding is an enormous amount of energy locked up in a form that moves slowly through space. But there's a deeper answer, and it has to do with something called the Higgs field. This is where things get really mind-blowing. The Higgs field is an invisible field that permeates all of space. Every cubic centimeter of the universe is filled with it, like space is filled with an invisible molasses. When particles move through this field, they interact with it, and that interaction is what gives them mass. Peter Higgs proposed this in 1964 as a way to explain why some fundamental particles have mass and others don't. Particles that interact strongly with the Higgs field have a lot of mass. Particles that interact weakly have little mass. And particles that don't interact at all, like photons, have no mass at all and can travel at the speed of light. Think of it like this. Imagine you're walking through an empty room versus walking through a crowded party. In the empty room, you can move quickly and easily. You have no resistance. In the crowded party, people want to talk to you, shake your hand, slow you down. The more popular you are, the more people cluster around you, the harder it is to move. The Higgs field is the party. Particles are people of varying popularity. Photons are so unpopular, they can walk through the party without anyone noticing them at all, allowing them to move at maximum speed. Electrons are a bit popular, so they get slowed down a little. Quarks, the building blocks of protons and neutrons, are more popular still, so they get slowed down more. This slowing down in the Higgs field manifests as mass. Mass is literally just resistance to acceleration, how hard it is to change a particle's motion. And that resistance comes from the particle's interaction with the Higgs field. So when photons become electrons and positrons in the Breit-Wheeler process, what's really happening is this. Two particles that don't interact with the Higgs field at all, photons, transform into two particles that do interact. with the Higgs field, electron, and positron. The energy that was in the photons gets transferred to the electron and positron, and their interaction with the Higgs field gives them mass. The discovery of the Higgs boson in 2012 confirmed this theory. The Higgs boson is a ripple in the Higgs field, like a wave on the ocean. Finding it proved the field exists, which means our understanding of how particles get mass is correct. And this leads to a staggering realization. Mass isn't fundamental. Energy is fundamental. Mass is just what happens when energy interacts with the Higgs field. Everything in the universe, including your body, is made of energy that's been slowed down by its interaction with an invisible field. You are not made of matter. You are made of energy that's dancing with the Higgs field. Now let's talk about something that's going to completely reframe everything we've discussed. Most of the mass in normal matter doesn't come from the Higgs field at all. Wait, what? I just spent several minutes explaining how the Higgs field gives particles mass, and now I'm saying it doesn't? Let me explain, because this is where physics gets truly bizarre. An electron gets all its mass from the Higgs field. If the Higgs field didn't exist, electrons would be massless like photons. But electrons are only a tiny fraction the mass of an atom. Most of an atom's mass is in the nucleus in the protons and neutrons. A proton is made of 3 quarks held together by gluons, the particles that carry the strong nuclear force. Each individual quark has very little mass from the Higgs field. If you add up the Higgs field-generated mass of all 3 quarks in a proton, you get about 1% of the proton's total mass. So where does the other 99% come from? It comes from energy, pure energy. Specifically, it comes from the energy of the gluons holding the quarks together and the kinetic energy of the quarks zipping around inside the proton at near light speed. Think about that. You have mass. Your body has mass. Most of that mass is in atomic nuclei, and most of that nuclear mass is literally the energy of particles moving and interacting inside protons and neutrons. EMC in action. You are made of energy in 2 ways. First, the fundamental particles have mass from interacting with the Higgs field, energy in one form. And second, the way those particles combine and move creates additional mass, energy in another form. This was discovered through decades of research in quantum chromodynamics, the theory of how quarks and gluons interact. But here's what will blow your mind. Some physicists think these experiments might produce something else too. Something called a photon-photon bound state. Remember photonic matter from earlier? What if, under certain conditions, 2 gamma-ray photons could bind together before converting into an electron-positron pair? Theory suggests this might be possible. The bound state would be incredibly short-lived, lasting maybe y-21 seconds. But during that time, you'd have a particle made entirely of light. It wouldn't be matter in the traditional sense. It wouldn't have mass, but it would behave like a particle. It would have structure, binding energy, quantum properties. It would be light acting like matter without actually becoming matter. These experiments are scheduled to start running in the next few years. We might be on the verge of creating and studying a form of matter that's purely photonic, that has no mass, that exists only as bound energy. This is the cutting edge of physics right now. This is where we're pushing the boundaries of what's possible. Now I want to bring this down to earth and talk about why any of this matters to you. Why should you care that light can become matter? What difference does it make to your life? Here's the thing. Understanding this relationship between energy and matter is the foundation of modern technology. It's why nuclear power exists. It's why PET scanners can image the inside of your body. It's why we can study the fundamental nature of reality. But beyond practical applications, there's something more profound here. Understanding that matter is energy, that light can become solid substance, that the universe is fundamentally made of energy in various forms. This changes how you think about reality itself. Look at your hand right now. The hand holding your phone or resting on your desk. That hand seemed solid, permanent, made of matter. But now you know better. Your hand is made of atoms, which are made of particles, which are made of energy interacting with fields. The electrons in the atoms of your hand are fundamentally the same type of thing as the photons from the screen illuminating it. Both are quantum fields in different states of excitation. The difference between the light you see and the matter you touch is not as absolute as you thought. They're cousins, not strangers. They can transform into each other, given the right conditions. The universe doesn't have a hard boundary between energy and matter. It has a spectrum, a continuum, with light at one end and what we call matter at the other. Think about what this means for your sense of permanence and solidity. Nothing is permanent. Everything is energy in motion, constantly vibrating, constantly interacting, constantly transforming. The atoms in your body weren't always in your body. 5 years ago, most of them were somewhere else. In food you ate, in air you breathed, in water you drank. 5 years from now, they'll be somewhere else again. You are not a fixed thing. You are a process, a pattern of energy that temporarily organizes itself into the form of a human being. You are light that learned to think. And if light can become matter, then matter can become light again. When you die, the atoms in your body will disperse. Some will be buried and become part of soil, and plants, and perhaps other animals. Some will oxidize and become carbon dioxide, eventually taken up by trees and turned into wood and leaves. Some will be transformed in ways we can't even predict. But those atoms, those frozen photons from the Big Bang, will continue. The energy that is you will continue, just in different forms. You are not separate from the universe. You are a temporary configuration of universal energy. And when your configuration dissolves, the energy returns to the cosmic ocean from which it came. This isn't sad. This is beautiful. You are made of starlight. You are the universe contemplating itself. You are 13.8 billion years of cosmic evolution that has organized itself to be conscious, to wonder, to ask questions, to seek understanding. Every thought you think, every feeling you feel, every choice you make is fundamentally a process of energy transforming and organizing. Your consciousness, whatever that is an emergent property of energy dancing in intricate patterns inside your brain. And that brings us to the really big question. What does all of this mean for consciousness, for free will, for the nature of reality itself? We need to talk about something that most physics documentaries avoid because it's controversial and we don't have definitive answers. What does the energy nature of reality mean for consciousness and human experience? If everything is energy, including your brain, including your thoughts, then what does that mean for you as a conscious being? Are your thoughts just energy transforming, no different in principle from light becoming matter? Is consciousness just another form that energy can take under certain conditions? These are questions that physics alone can't answer. They bridge into philosophy, neuroscience, and even spirituality. But what physics can tell us is this: the processes happening in your brain are physical processes. Neurons firing, neurotransmitters flowing across synapses, electrical signals propagating. All of this is fundamentally about energy transformation. When you think a thought, electrons are moving in your neurons. The mass of those electrons comes from their interaction with the Higgs field. The forces making them move come from electromagnetic interactions. The whole process is governed by the same quantum field theory that describes photons becoming electrons and positrons. Your thoughts are literally made of the same stuff as light. Not metaphorically, literally. The electrons carrying signals in your brain are siblings to the photons illuminating this screen. They're both excitations in quantum fields, both manifestations of energy. Does that mean consciousness is nothing special? I don't think so. I think it means consciousness is something energy can do under the right conditions, and that's extraordinary. Out of the chaos and violence of the Big Bang, out of the simple rule that energy can become matter and matter can become energy. Out of billions of years of stars forming and dying, planets coalescing, chemistry growing more complex somehow, energy organized itself to be aware of itself. Think about the chain. Photons in the early universe became quarks and electrons. Those combined into atoms. Atoms combined into molecules. Molecules combined into organic compounds. Those compounds organized into self-replicating structures. Those structures evolved over billions of years into bacteria, then plants and animals, then eventually humans. And now here you are, energy in human form, listening to words about energy and matter and light, understanding abstract concepts, feeling emotions, making decisions about your life. The same energy that exploded out of the Big Bang is now contemplating the Big Bang. The same photons that once filled the early universe, transforming into particles, are now organized into your brain, allowing you to understand how photons transform into particles. This creates what some philosophers call a strange loop, the universe examining itself through beings made of its own substance. Douglas Hofstadter wrote about this in his book, I Am a Strange Loop, exploring how consciousness might emerge from self-referential patterns in the brain. But here's where it gets even weirder. Quantum mechanics tells us that observation affects reality. The famous double-slit experiment shows that whether you measure which path a particle takes determines whether it behaves like a particle or a wave. The active measurement of conscious observation seems to influence physical reality at the quantum level. Does this mean consciousness plays a special role in the universe? Physicists argue about this constantly. The orthodox Copenhagen interpretation of quantum mechanics, developed by Niels Bohr and others, suggests that observation collapses the quantum wave function, turning possibilities into actualities. But what counts as observation? Does it require consciousness, or just any kind of interaction? Other interpretations, like the many worlds interpretation proposed by Hugh Everett, who was actually a student of John Wheeler, the same Wheeler from the Breit-Wheeler process, say that all possibilities happen, but we only experience one branch of reality. I can't tell you which interpretation is correct, because physicists don't know. What I can tell you is this: you are not separate from the physical processes of the universe. Your consciousness, whatever it is intimately connected to the energy and matter that makes up your brain. And that energy and matter are intimately connected to light, to photons, to the most fundamental processes of reality. When you look at sunlight, you're seeing photons that were created by nuclear fusion in the sun matter becoming light. Those photons travel through space for 8 minutes. They enter your eyes, where they're absorbed by molecules in your retina, triggering a cascade of chemical and electrical reactions that eventually create the experience of seeing light. Energy from the sun becomes energy in your brain, becomes the conscious experience of brightness and warmth. It's all connected. It's all one continuous process. And this raises the ultimate question. If everything is energy transforming, if consciousness is energy in a particular configuration, then what are you really? Are you the pattern of energy, which is constantly changing? Are you the process of energy transformation, which is continuous? Are you the awareness of that process, which feels unified and persistent, even as everything else changes? These questions don't have simple answers, but understanding that you're made of light, that your energy temporarily organized to be conscious, puts them in a new perspective. Let me tell you something that connects everything we've discussed to the furthest reaches of the universe and the deepest mysteries of physics, the cosmic microwave background radiation. Right now, if you could build a detector sensitive enough, you could detect photons that have been traveling through space for 13.8 billion years, photons that were released just 380,000 years after the Big Bang, when the universe cooled enough for light to travel freely. Before that moment, the universe was so hot and dense that photons couldn't travel at all. They'd be emitted and immediately absorbed by free electrons. Matter and radiation were locked in a cosmic wrestling match, neither able to escape the other. But then the universe cooled to about 3,000 degrees Celsius still, way hotter than anything on Earth, but cool enough for electrons to combine with protons to form hydrogen atoms. Suddenly, with no more free electrons to scatter off of, light could travel. The universe became transparent. Those photons have been traveling ever since, stretched and cooled by the expansion of the universe. Until now, they arrive as microwaves with a temperature of about 270 degrees Celsius, just 2.7 degrees above absolute zero. This is the cosmic microwave background, discovered accidentally by Arno Penzias and Robert Wilson in 1965, earning them the Nobel Prize in 1978. What this means is that you are literally bathed in light from the Big Bang. Every second, billions of these ancient photons pass through your body, photons that were there near the beginning of everything, photons that carry information about the early universe, encoded in tiny temperature variations. But here's the mind-blowing part. These photons have seen the entire history of the universe. They were there when the first atoms formed. They've witnessed every star that's ever ignited, every galaxy that's ever formed, every world that's ever existed. They've been traveling through space for longer than Earth has existed, longer than the Sun has existed, longer than our entire galaxy in its current form. And some of them just passed through your brain. Ancient messengers from the dawn of time, energy that's been propagating through space since before stars existed, interacting with the matter of your body matter that was once energy just like them. Think about the connection. The photons from the CMB were created when matter and energy first separated in the early universe. The atoms in your body were created later when stars fused lighter elements into heavier ones, releasing energy in the process. Both the photons and the atoms are products of the same fundamental process, energy transforming between different forms. And this is still happening. Right now, in the core of the Sun, hydrogen nuclei are fusing into helium, converting matter into light through EE, cools MC. Those photons take hundreds of thousands of years to random walk their way from the core to the surface, but once they escape, they reach Earth in just 8 minutes. Every second, about 4 million tons of the Sun's mass is converted into energy. That energy becomes light. That light illuminates Earth, warms the planet, drives photosynthesis, powers the weather, makes life possible. Without the Sun constantly converting matter into light, Earth would be a frozen, lifeless rock in space. You are alive because of matter becoming light. The food you eat was grown using energy from photosynthesis, which requires sunlight. The oxygen you breathe was produced by plants using sunlight. The warmth that keeps Earth habitable comes from sunlight. Remove the sun's light, and life ends. But it goes deeper. The very atoms that make up your body were forged in stars, and many of them were dispersed into space when those stars exploded as supernova explosions that temporarily outshine entire galaxies, converting enormous amounts of matter into light and energy. The calcium in your bones was created in a supernova explosion. The iron in your blood was forged in the core of a dying star. The carbon in your DNA was produced by nuclear fusion in a red giant star. All of these elements were scattered into space by stellar explosions, mixed with hydrogen and helium from the Big Bang, eventually condensing into new stars and planets, including the Sun and Earth. You are literally made of stars, not metaphorically. The atoms in your body were synthesized in stellar furnaces and supernova explosions. As Carl Sagan said, "We are made of star stuff." But it's more than that. We are made of light that became matter, that became stars, that became new matter, that eventually became us. Now let's talk about the future. Where is this research leading? What could humanity do if we truly master the art of converting light into matter and matter into light? Some physicists and engineers are already thinking about this. If we can efficiently convert light into matter, we might be able to manufacture materials from pure energy. Imagine a device that shines intense lasers at a point in space and creates atoms, any atoms we want, from the energy of those lasers. Need gold? Convert light into gold atoms. Need carbon for manufacturing? Make it from photons. Need hydrogen for fusion reactors? Create it on demand from light. This sounds like science fiction, and with current technology, it is. The energy required to create even a small amount of matter is staggering. To create 1 gram of matter from light, you'd need about 90 trillion joules of energy, more than all the energy used by the entire United States in about 15 minutes. So we're not going to be building matter from light replicators like in Star Trek anytime soon. But the principle is sound. If we could somehow harness enough energy and achieve the required precision, matter synthesis from light is possible. More realistically, understanding the matter-light relationship might lead to breakthroughs in energy generation. If we can create matter from light, we can also release that energy back out by converting matter to light. This is what happens in matter-antimatter annihilation, the most efficient energy release possible. When an electron meets a positron, they annihilate completely, converting 100% of their mass into light. For comparison, nuclear fission converts about 0.1% of mass to energy. Nuclear fusion converts about 0.7%. But matter-antimatter annihilation is 100%. If we could produce and store antimatter safely, it would be the ultimate energy source and the ultimate rocket fuel. A spacecraft powered by matter-antimatter annihilation could potentially reach significant fractions of light speed, making interstellar travel possible. The problem is making antimatter. Currently, we can produce it in particle accelerators, but the process is incredibly inefficient. For every particle of antimatter we create, we expend millions or billions of times more energy than we get back from annihilating it. But if we perfect the Breit-Wheeler process, creating matter-antimatter pairs from light, and if we can develop better ways to trap and store antimatter, we might eventually create a closed cycle. Use light to create antimatter. Use antimatter annihilation to create light and energy. Use that energy to create more antimatter. This is decades or centuries away from being practical, but it's not impossible. It's just really, really hard. There's also the possibility of using photonic matter light that acts like matter for practical purposes. If we can make photons bind together and create structures, we might be able to build optical computers that process information at light speed, quantum computers that use photon-photon interactions for logic operations, or even materials that can be. But the practical challenges are immense. Creating a single hydrogen atom from light requires converting 2 photons into an electron-positron pair, then somehow getting the positron to annihilate with another electron, while the first electron combines with a proton. Creating complex organic molecules would require coordinating trillions of such processes with atomic precision. It's not happening anytime soon, but it's not impossible forever. Let me bring this back to the present moment and give you something practical you can do with this knowledge. You can actually observe the relationship between matter and energy in your everyday life if you know where to look. Right now, if you're indoors, look around the room. Almost everything you see is visible because of light bouncing off matter. But that light is also interacting with the matter at a quantum level. Photons are being absorbed by electrons in atoms, boosting those electrons to higher energy levels. Then the electrons drop back down and emit new photons. The color you see is determined by which photons get absorbed and which get reflected. A red object looks red because it absorbs blue and green photons, but reflects red ones. The process of absorbing a photon is the reverse of emitting one. It's a transformation between light and the energy state of matter. When you touch something and feel its warmth, you're feeling infrared photons being emitted by the vibrating atoms in the material. Temperature is literally atomic vibration, and that vibration creates light in the infrared spectrum. You don't see it, but you feel it as heat. When you look at the sun, please don't stare directly at it. You're seeing the result of matter-to-light conversion happening 93 million miles away. Every photon that reaches your eyes was created by nuclear fusion, converting hydrogen into helium and releasing energy. When you turn on a light bulb, electricity flows through a filament or excites a gas, causing atoms to emit photons. You're witnessing energy transformation in real time. Electrical energy becomes light energy, and that light energy enters your eyes and becomes chemical energy in your retina, then electrical energy in your optic nerve, then neural activity in your brain. It's all connected. It's all energy transforming from one form to another, dancing between matter and light, constantly converting and reconverting. And you can think about this when you interact with the world. Every time you see something, you're catching photons that have bounced off matter. Every time you feel warmth, you're sensing infrared photons. Every time you eat food, you're consuming matter that was built using light from the sun. Every time you breathe, you're taking in oxygen that was created by plants using sunlight. You are embedded in a web of energy transformations. You are not separate from this process. You are part of it. Your existence depends on light becoming matter, becoming food, becoming the atoms of your body. And someday, when you die, those atoms will disperse and the energy will continue its cosmic journey. This isn't depressing. This is the most profound connection you can have with the universe. You are not a separate entity observing the universe from outside. You are the universe experiencing itself from the inside. And knowing this, truly understanding that you are made of light, that your very substance is frozen energy from the Big Bang, that you are temporarily organized stardust contemplating the cosmos, this should give you a sense of wonder and significance. You matter, not just in the sense of being important, but in the sense of being matter-organized energy that has achieved consciousness. You are light that can think. You are the universe examining itself. Before we wrap up, I want to address something that often comes up when people learn about this topic: the spiritual and philosophical implications of light becoming matter. Many spiritual traditions have metaphors about light and enlightenment, about humans being light beings, or about divine light. Buddhism talks about the clear light of consciousness. Christianity has imagery of God as light. Hinduism speaks of enlightenment as realizing your essential nature as consciousness, which is sometimes described as luminous. I'm not going to tell you these are literally true or literally false. What I will say is that the scientific reality that we are made of energy, that light and matter are intimately connected, that consciousness is an emergent property of energy organized in certain ways. This reality is profound enough without needing to add supernatural elements. But I also won't tell you that science has all the answers about consciousness, meaning, or purpose. Science can tell you how photons become electrons. It can't tell you why there's something rather than nothing, why the laws of physics are what they are, or whether consciousness has significance beyond being an emergent property of matter. These are questions that each person must answer for themselves. But understanding the science gives you a better foundation for thinking about them. Some people find the materialistic view depressing, the idea that we're just atoms, just energy, just complex chemical processes. But I find it liberating and awe-inspiring. You're not just atoms. You're atoms that can ponder their own existence. You're energy that has organized itself to be conscious. You're stardust that can look up at the stars and understand where it came from. The fact that this is happening through natural processes, through the laws of physics, doesn't make it less miraculous. If anything, it makes it more miraculous. The universe doesn't need supernatural intervention to produce consciousness. It can do it through the elegant dance of energy and matter, following simple rules over billions of years. And that's beautiful. That's profound. That's worthy of wonder and reverence. You are a way for the cosmos to know itself. As Carl Sagan said, you are the universe experiencing itself subjectively. and the mechanism by which this happens: energy transforming between light and matter, organizing into increasingly complex structures over eons, is as close to magic as reality gets. So let's bring this all together. Is there a form of matter made only of light? Yes, multiple forms actually. First, there's the Breit-Wheeler process, where photons collide and create electron-positron pairs. Light becomes matter in the most literal sense. Photons disappear, particles with mass appear. This has been observed indirectly at facilities like Brookhaven National Laboratory, and direct observation using laser light is likely coming within the next decade. Second, there's photonic matter, where photons bind together and behave like particles while remaining photons. This has been created in laboratories using ultra-cold atoms as a medium. Light acts like matter without actually converting into conventional particles. Third, and most profound, there's you. Every atom in your body was created through energy-matter transformations. The particles that make you up were once photons in the early universe. They transformed into matter through the natural version of the Breit-Wheeler process in the Big Bang. Some of those particles later became parts of stars, which fused them into heavier elements while converting matter into light. Those heavy elements were scattered by supernova and eventually assembled into planets and life. You are matter made from light, not metaphorically, literally. Your fundamental particles were once pure energy, and they can become pure energy again. The boundary between matter and energy, between light and substance, is not absolute. It's permeable, crossable, fluid. The universe doesn't recognize a hard distinction between them. They're both manifestations of quantum fields, both forms that energy can take. And this tells us something profound about reality. It's not made of stuff. It's made of patterns of energy in various configurations. Light is one pattern. Matter is another pattern. You are an incredibly complex pattern, organized over billions of years of cosmic evolution. The chair you're sitting on, the phone in your hand, the planet beneath your feet, all of it is frozen light, energy in stable configurations that we call matter. And the light illuminating this moment, whether from the sun or from a bulb, that's what matter becomes when it's liberated, when it's allowed to travel at its natural speed, unencumbered by the Higgs field or by being bound in atoms. We are living in a universe where light becomes matter and matter becomes light, where energy transforms endlessly between forms, where the distinction between substance and radiation is just a matter of configuration and interaction with fields. And we, you and I, human beings, conscious entities, we are the universe contemplating this transformation. We are patterns of energy that have become complex enough to ask, what are we made of? And to discover the answer, light, energy, the same stuff that fills the cosmos, now organized to think and wonder and understand. This is the truth that physics has revealed over the past century. It's more extraordinary than any myth, more profound than any fiction. Reality is strange enough, beautiful enough, connected enough that we don't need to invent stories about our significance. We are significant because we are consciousness emerged from cosmos, light transformed into life, energy organized to understand itself. You are made of light. You are light made conscious. And now you know it. So here's what I want you to take away from these past nearly 3 hours we've spent together. First, remember that the solid world around you is not as solid as it seems. Matter is energy in configuration stable enough to persist. Light is energy in its freest form. The two can and do transform into each other, following the elegant mathematics of EMC. Second, remember that you are connected to everything in the universe through this fundamental relationship. The atoms in your body were forged in stars. The energy animating you came from the sun, which came from matter to light conversion. The photons you see were created by energy transitions in atoms. You are embedded in a cosmic web of energy transformations. Third, remember that science is still discovering new things about this relationship. The Breit-Wheeler process was predicted 90 years ago, but is only now being directly observed. Photonic matter was created for the first time in 2013. We're living in an age where theoretical predictions are becoming experimental realities, where the boundary between science fiction and science fact is blurring. Fourth, remember that understanding this doesn't diminish the wonder, it enhances it. Knowing you're made of stardust and light doesn't make you less special. It makes you more special because it connects you to the entire cosmos. You're not separate from the universe. You're an integral part of it. And finally, remember that there are still mysteries. We don't fully understand consciousness. We don't know why the universe exists. We don't know if there are forms of matter or energy we haven't discovered yet. We don't know what dark matter and dark energy are, even though they make up 95% of the universe. Science is an ongoing process of discovery, not a finished body of knowledge. What we know today is vastly more than what we knew a century ago, but it's probably vastly less than what we'll know a century from now. You're living in a time when we're pushing the boundaries of understanding, when we're creating matter from light in laboratories, when we're probing the fundamental nature of reality. That's exciting. That's something to be part of. So the next time you look at light, whether it's sunlight streaming through a window, the glow of a screen, or the beam of a flashlight, remember what you now know. That light is energy in its purest form. And under the right conditions, it can become matter. It can become atoms. It can become stars, planets, and ultimately, living beings. You are made of light. You are the universe examining itself. You are energy that has become conscious. And that is absolutely mind-blowing. Thank you for spending these hours with me exploring one of the most profound questions in physics. If this has changed how you see the world, if it's given you a sense of wonder and connection, then my goal is achieved. Don't forget to like this video, subscribe to the channel, and share your thoughts in the comments. Tell me what blew your mind the most. Tell me what questions you still have. Tell me how this changes your perspective on reality. And remember, every time you see light, you're seeing pure energy. And every time you touch matter, you're touching frozen light. You are light. The universe is light. Everything is light in various disguises.